In this tutorial example, a stone is thrown from the top of a building upward at an angle of 30 degrees to the horizontal with an initial speed of 20 meters per second. The height from which the stone is thrown is 45 meters above the ground. So we are to determine how long it takes for the stone to reach the ground and the speed of the stone just before it strikes the ground. So bear in mind that this is a projectile motion problem, and because it is a projectile motion problem, it is always beneficial to the solver to visualize the path of the stone as it is thrown and as it reaches the ground. So let's say this is the stone at initial, and this is say 45 meters above the ground. It is thrown with a speed of 20 meters per second at an angle of 30 degrees from the horizontal. So remember that when dealing with projectile motion problems, it's like analyzing two different motions, one on the x-axis and one on the y-axis. So we imagine that the stone, idealized as a particle in this solution, is moving along the x-axis at a speed of vx, and moving along the y-axis at a speed, okay, at a speed of vy. Now remember that this Vx and this Vy are basically just the x and y components of our velocity vector. And when we visualize this as a right triangle, okay, see this theta, this is Vx and this is Vy, and therefore Vx is just equal to V cosine theta, and Vy is just equal to V sine theta. Alright, so then we have two different bodies moving at two different speeds on two different axes, two different paths, but when added together they move in a path similar to this, loosely visualized as something like this, that reaches the ground. Okay, so the answer, letter A, we will use the kinematic equations, and one of those kinematic equations is yf is equal to yi plus vyt plus 1/2 at squared. Now remember, the y we're using is the x component of a y, and the yf will be, or the final position of the stone relative to the origin of the y component. Okay, since this is 45 meters and we say that this is the origin, it's 45 meters below the origin, so therefore this will become negative 45 meters, and so yi starts at the origin, so this is 0, plus 20 sine 30 t plus 1/2 times negative 9.8 t squared. So solving for t, when you use your calculators, you will find that t is equal to 4.22 seconds. Okay, now moving on to B, we want to know the speed of the stone just before it strikes the ground. So just before it strikes the ground, remember that this is traveling at a substantial speed, and we see that it is slanted again, and therefore we can break this apart into x and y components. So this is Vx, and then this one will be Vy. Now remember, Vx here and here will remain the same. Why? Because there is no acceleration that is affecting the x component of our stone, of the speed of the stone. However, for Vy, it will change because of the presence of gravity in our kinematic solution. So therefore, all we have to do to find, let's call this VF, all we have to do to find VF is just take the square root of VXF squared plus VXY squared. Now VXF squared is the same as VXI, so that is V cosine theta. But VXY, we have to find that. Now since we have time already, now to find no, that's not VXY, that is VYF. To find VYF, we will just use this kinematic equation. VYF is equal to VYI plus AT. Okay, so then we will have 20 sine of 30 plus negative 9.8 times 4.22, and therefore we will have VYF as a negative 31.3 meters per second. Plugging this in to this equation. Now remember that this equation is just from the Pythagorean theorem. Okay, so then we will have VF is equal to square root of V 20 sine 30, cosine 30 squared plus negative 31.3 squared, and therefore our VF is just equal to 35.8 meters per second.